See, next concept is, in the earlier circuit we have used some resistor, okay, uh, or some current source, right? Here, direct current source. What you are going to do is, the I'm going to replace your like a resistor into some active devices. Okay, this active device is going to provide the constant current source. Okay, you can see here I explained you clearly. The MOSFETs can be configured act like a resistor, okay, that can provide some reference current. Okay, so usually established by using the additional transistor. Before we are using two transistor, here I have used the another one, that is a third transistor. The purpose of adding this transistor is to provide the constant current source. Okay, so that I can increase the stability in the circuit. Okay, so here you can see here M1 and M3 are in series, right? M1, so IRF current equal to same current is passing through here also. You know that gate is 0. Okay, same current ID3 current will go to ID1 also. Okay, so this is biased by VGS1. Same bias voltage was given to this M2 also. So the current will be same. Okay, that is our understanding what we learned in the previous classes. Right. So here thing is both the transistors are in series. M1 are equal to M3. Okay, so what you will get, so when you write like that, I drain current is equal to ID1 is equal to ID3, I said clearly. So here you have a ID3, here you have a ID1, both will be equal. So if you write both are equal, Kn1 VGS1 minus VTN whole square equal to Kn3 VGS3 minus VTN3 whole square. Okay, now you apply the KVL. Okay, when you apply the KVL, when you apply the KVL in this circuit, you apply in this loop. Okay, so I'll put separately, like here you have a minus plus, that is a V plus, right? Then this part is your VGS1 plus minus. Okay, so this is written plus minus, then this drop. So it should be VGS3, right? It should be VGS3. VGS3. Then you have a next to drop. Just for your understanding, I am redrawing this loop. VGS1 plus minus. Then this negative supply. Okay. V minus plus minus. You apply the KVL in the clockwise direction. What you'll get? What you'll get here? Minus to plus. I'm used to take a leaving symbol here. Okay, plus V plus. This plus is for this one. Entering at a plus, leaving at a minus. So minus, this minus for this one. This drop is VGS3. Then entering at a plus, leaving at a minus. Minus VGS1. Entering at a plus, leaving at a minus. So minus V minus. So equal to 0. If you rewrite this equation, what you'll get? V plus minus of V minus equal to, you bring this two term to the right side, so it will become positive. VGS3 plus VGS1 equal to 0. So this is a very important equation we will be using in all numericals. Okay, so V plus minus of V minus equal to, this is in the superscript. Okay, this is the superscript. VGS3 plus VGS1. So this is the way how this equation was obtained here. You can see here. So this is a very important equation you want to remember. Okay, so next what I am going to do is, they got this equation after calculation. How? I'll explain this part. Okay, very simple. So this what we studied, right? Kn1 Vgs1 minus Vtn whole square equal to Kn3 Vgs3 minus Vtn3 square. This is M1 transistor, M3 transistor are equal. With that assumption you are writing. What we are going to find is what is your VGS2. That's all. So that voltage is making your M2 to saturation. That is our understanding. Okay. So we know that all parameters or physical parameters are constant. Okay. The W by L ratio alone I am taking as a different. Okay. I am, so that this equation all terms will be get cancelled. Both are same, right? Both are physically, all parameters are same. So that W by L1 Vgs1 minus Vtn whole square equal to W by L3 Vgs3 minus Vtn3 whole square. With this one, I'm taking this as a different, and remaining all are same, so all will get cancelled. So here I'm rearranging the equation. If you rearrange this equation, so what you'll get, W by L3 Vgs3 minus Vtn3 whole square, this will come down, right? Then I am bringing this square to this right side, so it become W by L3 3 Vgs3 minus Vtn3 square divided by W by L1. Then this square and this square will get cancelled. So now the square root only for these two terms, not for this, because this will get cancelled. So I can write like a Vgs1 minus Vt1 equal to square root of W by L3 W by L1 into Vgs3 minus Vtn3. Okay, so your root of x is equal to what, I am just for our simplification I am taking like a root of x is this whole term, I can take it as a root of x equal to root of W by L3 divided by W by L1. So hereafter for our derivation we will be taking this whole term as a root x. Okay, with that assumption it was written like a Vgs1 minus Vtn equal to root x Vgs3 minus root x Vgsn3, right? I can write like that, right? I can write. So I have just multiply and this whole term is written as a root x. I hope it was clear. Only for your understanding it was written like that. So then I bring this minus Vtn to the right side. So it become Vgs1 equal to square root of x Vgs3 minus square root of x Vtn3 plus Vtn1. Here I am taking this your this Vtn1 equal. Okay, because both are identical, so Vtn1 both will be same. So here in these two terms I am taking this Vtn common, so that you will get 1 minus root x. So here root x Vgs3. Already we learned, I explained you how you get this equation, that is Vgs1 plus Vgs3 equal to V plus minus of V minus. From here I can rewrite and I can show Vgs3 equal to V plus minus of V minus minus Vgs1. So substitute here. Substitute this equation. So this equation becomes Vgs1 equal to square root of x V plus minus of V minus minus Vgs1 plus 1 minus root x Vtn. Okay. So here from this I am bringing this Vgs term coefficient to the left side. So you can see you have one coefficient. So bring to the left side. So it becomes Vgs1 plus square root of x Vgs1 equal to root x V plus minus V minus plus 1 minus root x Vtn. Okay, here I am taking Vgs1 common. So Vgs1 into 1 plus root x equal to root x V plus minus V minus plus 1 minus root x Vtn, this whole term. I am dividing this whole equation by this term. So it becomes this like. See, now you substitute this x root x like you know that we assumed root x equal to w by L3 divided by w by L1. So I'm substituting here. Okay, so that equation was written like this. Okay, this equation only they have written here. Okay, directly it was derived in the book. Here you have explained you step by step. Okay, then we know that your so both will be saturated, like your M1 will the same VGS is given to the VGS2, so your M2 also is going to the saturation condition, so that your output current will be K dash N divided by 2 W by L2 VGS minus VTN square. Here the channel length modulation I am not taking, so that's a lambda is 0, so finally you are getting I not equal to this whole term. Okay, this is about the replacement of Mosfet. Okay, the next topic is cascoded current mirror. Okay, so already I said the task is, you know clearly, there is a change in the ID with respect to VDS. So obviously we have a channel length modulation, it will be larger. So as much possible I want to suppress by going to the by doing modification means there is a next topic is cascoded current mirror. Okay, I'm going to modify the existing current mirror and I'm going to take it as a cascoded current mirror, so that the changes of being here with respect to ID versus VDS can be suppressed. Okay, the first concept, only three objective why you want to go for cascoded current mirror. The thing is, I want to make VDS1 is equal to VDS2. Okay, I want to ensure that. Okay, I'm for that I'm introducing the cascode connection in your circuit. Okay, I'm adding series with the M2 transistor. Okay, that I'll show in the circuit, that is in the output stage. Third, the stability will increase. Okay, stability change in the drain current with respect to VDS to be minimized. These are three objectives we are going to discuss. Okay, so very clear. See, this is your normal cascoded current mirror. Okay, first let me explain you what are the things are necessary here. This is a current mirror concept. Okay, this is a current mirror. M1 and M2 is acting as a current mirror, and M4 I said it is a cascoded stage. For M2, M4 is cascode. Okay, here another MOSFET is used. M3 is used to drive the M4. Okay, so first let me we want to make I naught is equal to IRF. The changes in the VDS2 with respect to VDS should be suppressed. Okay, so we know that the gate voltage of M1 and M3 will be equal, and M2 and M4 are constant. Okay, this is in series and this is in the series. Okay, so this is something like a two transistor current mirror. This is one current mirror and this is another current mirror. Okay, this is one current mirror and this is another current mirror, like a stack of two mirror circuit. Okay, if you are considering all are identical, your I naught is equal to IRF. Okay, this is our assumption. So we will begin the concept like I will remove this M3. Okay, I will remove this M3 such that I want to give some bias voltage. So let me give some bias voltage. That bias voltage is making your changes with respect to the changes with respect to I naught will be suppressed. Okay, so that we will see now. See, let me take like this. See, now I have removed this M3 transistor. I have placed only M4. This is a cascoded connection. This is a cascoded connection with the M2. So I am giving some bias voltage. I am giving some bias voltage. This bias voltage is trying to you take this is your Vx point and you take this is your Vy point. Okay. So we know that Vx is nothing but your VDS1 and Vy is nothing but your VDS2. So what you want to understand is the changes of VDS2 with respect to I naught should be reduced. That means I want to make your Vx is equal to Vi. So what I am going to do is I am going to use some bias voltage. Okay, some bias voltage such that the changes of in the output stage will be compromised with respect to VDS2 with respect to I naught will be compromised. With that your Vx will be equal to Va, I can prove. Okay, so what is that bias voltage? First you want to generate. What is the bias voltage here? That is VGS4 plus Vx. Okay, how I got this one? We want to go from the step by step. Okay, so this is your M4 transistor. So this is your like a VGS4, right? VGS4. VGS4. So this point is your VG. This point is your VS, right? This point is your VS4. Right, so this is your VG4, this is your VS4, right? So VS4 and this is your VG4, so VG4 minus VS4, right? So we know that this VG4 is nothing but your VB, so I can write like a VG4 is equal to VB, so I can write like that. VS4 I can write like a VY, VS4. So with that it was replaced like a VB minus VY. VB minus VY. Right. Already we learned VDS2 equal to Vx, and here this point. This point is here VDS VDS1 equal to Vx. Here VDS2 equal to Vy. So with that assumption it was written. So VDS1 equal to VDS2 and Vy equal to Vx you want to consider. Okay, so if you rewrite this equation, so here like I am rewriting this equation, so that is from the first equation. From the first equation I am writing the VB, so Vy will come to the left side, so it becomes VB equal to VGS4 plus Vy. So we know that Vy equal to Vx, so with that assumption your VB equal to VGS4 plus Vx or VGS4 plus VGS1. We know that VDS1 is equal to VGS1, right? Because both are shorted. So this VDS1 and VGS1 both will be shorted because that too in the saturation condition. Okay, now see we have made all assumption and we have find that your bias voltage should be VGS4 plus Vx, right? I hope it was clear. So VGS4 plus Vx. Okay, now you bring the assumption like a VDS1 is not equal to VDS2. So I want to introduce this bias voltage so that I can minimize the changes of drain current with respect to VDS2 can be done. So VB equal to VGS4 plus Vx. Okay, so you apply the KVL in this loop. What you'll get? You apply the KVL. What you'll get? So this point is VB. Then this point is your VGS4. VGS4 plus minus. Then down point is your VY. Apply the KVL in this loop. What you'll get? See VB, VGS4 and VY. So this only done here. So when you apply the KVL, what you'll get? Minus 2 plus. So VB plus VB, entering at a plus, leaving at a minus. So minus VGS4 minus Vy equal to 0. So this equation I have written here. So Vb minus Vgs4 after applying the KVL. KVL equation. So Vb minus Vgs4 minus Vy equal to 0. So what is the Vb? We learned Vgs4 plus Vx. Okay. So if you substitute, both will get cancelled. So Vx equal to Vy. Okay. So the understanding is I want to give the this bias voltage so that the changes of VDS2 with respect to I0 will get cancelled, so that Vx will become Vy. So that is VDS1 is equal to VDS1. So that is the concept of this cascode configuration circuit. Okay, so this is the first concept is completed. Next is how to show like how the impedance was increasing in the cascoded configuration. Okay, for that I have taken this basic circuit. So this is your like a M1 and M3, both are in series. This are in the series. Okay, so this will be in series and this will be in series. I have given the reference current and this is your output current. Okay, here first step I am going to draw the small signal equivalent circuit. Okay, okay, and considering this part some DC voltage, constant DC voltage. Okay, I can put like this some battery, because this is something like a DC voltage, right? It's a constant voltage only, no? So I can replace some battery like this. So when you draw the small signal circuit, you know that you want to remove all the DC supply, right? So I am removing all DC supply. What I have done is this Mosfet I have replaced to the some constant voltage source, because it is something like a constant DC voltage only. It is providing some constant DC voltage, so that's why I am replacing this Mosfet into the DC voltage. That then I am removing, because to draw the small signal equivalent circuit. So this will become grounded and this also will become grounded. So I am remove the supplies. So this whole circuit is replaced like this. Will be replaced like this, right? So you can see here this whole circuit was replaced like this. So M1 and M3 are removed, because this is actually those was considered as some constant DC voltage and removed from the circuit. So to find the output resistance, I am considering this circuit further. So here M2 and M4. Okay, here and I'm applying some testing voltage. Let it be like a Vx. The current is Ix. So output resistance can be calculated by R naught equal to Vx by Ix. Okay, so your output resistance will be Vx by Ix. Okay, so first you draw the equivalent circuit for this circuit, right? So when you draw the equivalent circuit, so you will be having here, you will be having your G4, right? Here you will be having the S4. So G4 and S4, right? See, first let me draw for normal MOSFET. So gate, drain, source. If you draw the equivalent circuit, what you will have? You will be having a gate and drain, source. This is your VGS and this is your GM-VGS4 plus here you have a resistance. So same model you want to represent here. For M4 it is represented here. For M4 it is represented. Down also you will be having the you will be having GM VGS2. Okay, but you can see here it is connected to ground. Your G2 is connected to ground and source also connected to ground. Okay, so G2, this is G2 and here you will be having a S2. Both are connected to ground. So obviously this also is going to be a 0 only. So no meaning like to consider this terminal, right? So I removed from this circuit, I have taken only the resistance. So repeating again, your gate and source are connected to ground. So this current term will be 0, right? That's why I removed this GM2 and consider R02. With that consideration only, this was redefined and drawn like that. Okay, now I'm applying the KCL to this equation. So when you apply the KCL to this equation, this current term is coming outside, this current term coming outside. So Ix equal to this term plus this term. Okay, so what you'll get, Ix equal to GMVGS4 plus GMVGS4 plus Vx minus of this drop, minus, we want to look from this minus polarity, so minus VGS4 divided by this R04. Okay, so what is the equation you'll get? So when you apply the KCL equation, you will be getting Ix equal to GMVGS4 plus Vx minus of minus VGS4 divided by R04. So because why in the minus? Because you are looking for the negative terminal. You are looking for the negative terminal, that's why minus VGS4 is coming. So Ix equal to GMVGS4 plus Vx minus of minus VGS4 divided by R04. Okay, so here I am introducing like a VGS4 equal to minus Ix R02. Why? Because I am applying the KVL here. Okay, so let me erase all the notations. Okay, you apply the KVL in this part. What you'll get? What you'll get? My entering at a plus, leaving at a minus, minus VGS4 minus entering at a plus, leaving the current term is Ix R02, so equal to 0. So when you rewrite VGS4 equal to minus Ix R02, so this only I am taking here. So you can see here. Okay, so then I am substituting here and here. Okay, so after substituting and rearranging the equation, you will get Ix plus R02 divided by R04, Ix plus Gm R02, Ix equal to Vx by R04. Okay, after rearranging the terms, that you can try. Okay, very simple. And taking Ix common, if you take Ix common, what you'll get? You'll be getting 1 plus R02 divided by R04 plus Gm R02. Okay, then I am bringing this Ix down and bringing this R04 to this side, so that your R04 will come here, plus R04, R04 cancel, so R02 plus Gm or it will be cancelled, right? So we will be getting this term. So Gm R02 R04 you will get. Okay, from here, so what they are trying to do is they're taking here R02 cancel, na? So in this step I will put. So what you'll get? So when you write, so R04 plus, so R02 into R04 divided by R04 plus Gm R02 R04. So we'll be get cancel. So with that only the R04 plus R02 plus Gm R02 R04 is coming. From here I can take R02 common, so that you'll get R02 into 1 plus Gm R04. So you got a Vx by Ix, so that is your expectation to find output resistance. So Vx by Ix equal to R04 plus R02 into 1 plus Gm times of R04. Okay, so here I am bringing another assumption. So R04 plus R02 plus Gm R04 into R02. Okay, so I will write here. So R0 equal to R04 plus R02 plus Gm R02 R04. This compared to this term will be larger, because you can see the product of Gm R01 R04. With that assumption, this will be removed from this equation, and approximately R04 equal to Gm R02 into R04. Okay, so what you finally understand is the resistance was increasing when you go for the cascode, the stability was increasing, and also by choosing the proper bias voltage, the changes of VDS2 with respect to I naught also can be minimized. And another thing, this bias voltage was feeded through M3 transistor by finding the bias voltage, right, mathematically. Okay, so that is about a cascoded current mirror.